In this video, we're going to focus on designing finite state machines using a one-hot encoding. That's the case where only one of the state variables could be on at any given point in time. So, which means basically if you have 5 states, you need to have 5 flip-flops to implement the finite state machine. And we're going to use Dflipflop. The reason we're going to use Dflipflop is our goal here is to demonstrate the one-hot encoding and don't want to get trapped in trying to figure out a more complex flip-flop. Dflipflop is easy because the characteristic function d equals to y plus equals to d is very simple to use. Okay, so let's go ahead and go through it. And as we've talked about before, our focus really is going to be from step 1 to step 5 in these videos. Once we get to step 5, we have the schematic, and once we have the schematic, we can implement it and test it. So that's our focus. Okay, so let's go ahead and talk a little bit about what we're going to implement. We're going to implement this new racetrack light. These are the light at the beginning of racetrack, which tells the driver to be ready, go, and a few other things in the middle. So we're going to have a red light at the top, then we're going to have a orange light, then a yellow light, then a green light meaning a go as the last step. And once the red light changes, it's going to go every 5 seconds. It's going to change color from one to the other until it goes to green and everybody's ready to go. So since our intervals are 5 seconds, we're going to just basically, just to make our life easier, we're going to use a clock. We're going to use a clock that basically has a period of 5 seconds, and that makes our life easier. Okay, and in the previous videos we've discussed how to design and build timers. So now the question is what we're going to do. We're going to basically go back here, and we're going to follow this process that was laid out for us. The first step in the process is to read the description of the problem, understand the description of the problem, do a system diagram, and then do a state diagram. Okay, so we're going to read this. It says one-hot encoding is what I want to use. I'm trying to design this thing, and it looks to me like I have to have a state which is red light, I have to have a state which is yellow light, I have to have a state which is orange and then yellow light, and then green. And then every time a start button is pressed, that process gets started, and once I get to green, stay green until somebody presses the start button. So before we go too far, let's go ahead and see if we can put this into a system diagram format. So from my point of view, what the system diagram looks like is that we've got one input, and then we've got 1, 2, 3, 4 output. We've got the red light, we've got the orange light, we've got the yellow light, and we've got the green light. And the input, the only thing we have is start, or let's just use S so it's simpler to use it. So S is our external input. Great. So now the question is, can we use this to do a state diagram? Well, the state diagram potentially could be, we have where the red light being on could be a state, and then and obviously we might as well say in this state, then the red would be on, everything else is off. Then I'll just put the red in here. Our input, we don't, so it looked like every time a start is pressed, we should end up in red. So this is a shorthand. You put a start in here, and you say S. So anytime S is pressed, you come in here, and so S equal to 1 basically. We come here. All the other time when S is equal to 0 and clock, we'll just keep switching. If it's red, clock comes along and S is not equal to 1, then we'll go over here. So S equal to 0 goes to, I think we said red goes to orange and then yellow. Yep. So you go to orange here. Okay, orange. And then, or of course, the orange light will turn on. And then if S still 0, then we'll go to yellow. And of course, the yellow light will turn on. And then we'll go to green state, where green light will come on. And then we'll basically sit here as long as S is equal to 0. So that looked like a good state diagram. So we're done. We've kind of described, we read the description, we turned it into a system diagram so we know what the inputs and the outputs are, and we have a picture that describes for all possible input what state goes to what state. So let's see what's the next step. So this was one first step. We completed the first step. Determine the number of flip-flop based on the number of states. So we need to decide whether we want a full encoding or one-hot encoding. In this case, we want to focus on one-hot encoding because that is the title of this presentation, and that's what they asked us to do in the problem. So great. So we are doing one-hot encoding, which basically means only can have one state variable on for every state. Since how many states do I have? I have 1, 2, 3, 4 states, which basically means I have to have 4 flip-flop, because since for a one-hot encoding. Okay, so now okay, so I have number of flip-flop, assign one variable to each flip-flop. Fine, I'll just call them, so I have 4 of them, so we'll just name them, we call one Y3, one Y1, I'm sorry, Y2, Y1, and Y0, and these are my variables. Great. What's the next step? Next step is assign unique code to each state. So what happens is that if I have this and I'm doing one-hot encoding, the best I can do is these are the only states I have available to me to work, because all the other possibilities are invalid with one-hot encoding. So now I have to relate these to those states. So the states I have are red. So red gets associated with 1. Orange. So orange gets associated with 2, or Y1 being 1, and then yellow gets associated with 0, 1, 1, 0, 1, 0, 0, and green gets associated with the 1, 0, 0. Okay, so now my states are related to my code. That was what I needed to do in step 3, which says assign a unique code to each state. Now select the flip-flop type to be used. This one is kind of, we have three options. We can use Dflipflop, Tflipflop, or JK. In this problem, they told us we needed to use Dflipflop, which is kind of nice because that's the easiest one to use, simply because of the relationship being such a straightforward relationship. Y plus is equal to D, D is equal to Y plus. So I need to do a present state, next state diagram with the goal of writing the excitation input equations and the more or mealy output equation. Okay, so the simplest thing would be to go over here. I have done step, so we are on step 4 now. So for step 4, I need to do a present state, next state. So the question is, what are the present state, next step? The present state, next state really is that I will have Y3, Y2, Y1, Y0. These are my present state. I do have an external input. My external input is start. So this is my external input. Then I will have next state, But that's really not what I'm interested in, but I'll go ahead and, what I'm really interested in is basically um, the I'm sorry, what I'm interested in D. What is the value of D? But first you have to write the y plus, then use the y plus to figure out what the D is. So we're going to do y plus 3, y plus 2, y plus 1, y plus 0. Okay? And at some point, of course, got to come back and do the output. The outputs we basically have 4 outputs. We have the red, green, red, orange, yellow, and green. Because this is one-hot encoding, the outputs will really be simple because R is equal to Y3, is equal to Y0. I should probably write them in the same order so it's easier to remember. So it's going to be green, yellow, orange, red. And if you recall the way we picked the state 1, it will give us red, 2 give us orange, and 3 gives us yellow, and 4 gives us green. That's one of the advantages of going to the one-hot encoding, because typically the output and the state are the same and they drive each other, so you don't have to use any logic to create them. So I can just write the same, so we don't have to develop it. Same as Y's. Now, so let's do this first. So to do this, I have to have the state diagram in here. And I'm not going to write this out because it's got 5 variables. If I write the whole thing, that's going to be 32. There is no reason for me to write the whole thing. The only valid states are 0, 0, 0, 1, when this is a 1, and when this s is equal to 0, then 0, 0, 0, 1 when it's a 1. I could have even compressed this, but for now let's not do that. So 0, 0, 1, 0 with an input of 0, 0, 0, 1, 1. Oop, that's not a valid one. 0 with the output of 1, and then 0, 0, 1. 1 is in here. 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. Those are all the only states I care about. All other cases, I really don't care because they should never happen. And if it happens, some sort of an error occurred. So if I'm in state 1 and I get a 0, I'm supposed to go to 0, 0, 1, 0. If I get a 1, that's a star, so I have to go back to state 0, 0, 0, 1. And then we just continue on to state 2. If I'm in state 0, 0, 1, 0, I go to next state, and I'm just looking up here, as you see. And sometimes it may be helpful to take these values you just got and plug it into that state diagram, so it makes your life a little easier to when you do the conversion. Right now I'm looking at, so I see that I've got 0, 1, 0, 0, which is a yellow state. If I'm in yellow state, S is 0, I go to green, which is 1, 0, 0, and that's what I'm basically doing. If I'm in green and S is 0, I stay here. If it's gets a 1, then it goes back to 1. One thing I forgot to mention here, we need to really talk about that when output is equal to 1, then lights up, whatever the corresponding lights up. Okay, and then for the input, we should really say that S equal to 1 means the button is pressed. and 0 means not pressed. Okay, I should have done that to be complete. Okay, the other thing is I go over here and take a look at the Dflipflop. Dflipflop says that y0 and d are 5, that y and y plus and d is the same thing, so these are next state, but the excitation input's the same, d3, d2, d1, d0. That's why we kind of like this. Okay, so I wrote some kind of follow-up on this one just to make sure. So d0, d1, d2 are the excitation input. That's the ones we want to write the equation, because we're going to need that one in order for us to be able to design the schematic. y0 plus y1 plus y2 plus y3 plus came from the state diagram which we had drawn earlier. So, and then the output in this case, I forgot to write the whole thing, is the same as the present state. So really don't have to show much of anything. I just take the y0 and that becomes the output. And y0 becomes the red output, y1 becomes the orange output, and y2 the yellow, and y3 the green. Okay, so this gets kind of interesting in that all the other cases are don't care, and in the case of a one-hot encoding, you really either got, if you really want to minimize it, you use a Carnot map. If you don't really want to minimize it, then we can just go ahead and do it this way, because all the other possibilities are don't care for us. Okay, at this case I'll just write it. If there is some obvious minimization, we're going to do it. Otherwise we'll just leave it as it is. Okay, so let's go ahead and take a look at that. What I need, I need to be able to write the equation for d0. So I'm going to write the equation as d0, just two inputs. I'm either going to have y3, y2. So the only time that's a 1 is right here. With y3 is not, y2 is on, and then y1 and y0 are not. Okay, the only thing to remember is that if y2 is on, all the other state where y2 is on, it's a don't care. Okay, even though this is the only case that I have, I could potentially write it as simply y2. Does that make sense? But just got to remember that you're assuming all the other states never happen, because it's a one-hot encoding. You should never, as you can look at your diagram, you never end up in a state where you got more than one output variable on at a time. And then the next one is the case down here where we get a oh, I'm sorry, there's one other variable I have to put in here, and that's s is not. Okay, and then oops, actually that's d3 I'm writing, which happened to be equal to y3 plus for this column right here. And then the other place is right here where it's a 1, and that is where y3 is on, and then everything else is off. And S is off. Okay? So again, I don't know if you follow I said it clearly enough, but I want to make sure I emphasize it again. All the other cases we haven't written, all the other possible states we haven't written are don't care from our point of view, because they never happen. So I simply could take this thing and rewrite it as y2 s naught or y3 s naught. Okay? Now, using the same philosophy, this time I'm not going to write the whole thing, just going to jump to it. When I look at D2, I find that D2, which is equal to Y2 plus, now here, Y2 plus, we're going to have just one instant, and that is when Y1 is true, S is not pressed, and that's it. Okay, and then we go to D1, and in the case of D1, there's only one that happens, and that is when Y0 is true and S is not. Okay. Now, let's see what else we got going. D0 is the last one we gotta do, and D0 has got every other one, as you can see here. And if you imagine, it says, okay, Y1. So we could, it look like in every case when S is equal to 1, we jump to that state. And since we don't care about the rest of them, D0 is just simply S. Okay. Anytime S is not pressed, when the clock comes along, we're going to end up in Y0, which happens to be D0. Okay. So now I have that, and just as a reminder, this is called the excitation input equation. Excitation input equations. The next one is the external output. As we mentioned, in this particular case, the external output becomes somewhat easy because we could just say green is equal to Y3 and yellow is equal to Y2 and orange is equal to Y1 and green is equal to Y0. Once I have done this, then the schematic becomes really easy. I've got 3 flip-flops. Let's make this a little, and I'm not going to show the clocks. The clocks are there and they're running into to the flip-flop. So in this case, I have 4 flip-flops. Because it's called D0, D1, D2, and D3. We got Y0 coming out of here, Y1 coming out of here, Y2 here, and Y3 here. We've got a start, which is our input. And as you can see, if this is the start input, the D gets the start, and then this gets inverted and comes down with this ended, gives us the D1. And then it gets ended with Y1 to give us D2. And as we continue on, then we have Y2 and S0. Okay, and so that comes in, then Y3 we bring back, and that. These get OR together, and that gives us the D3. So we got that done, and the outputs are really simple. The outputs, one is gonna be from here, another one is gonna be from here. Not there. Got carried away. Another one from here, and This looks, yeah, that's right. Y2, sorry, this is incorrect as well. So this has to go up here. This has to come down and together, and that goes in here. Okay, and this is an OR. I'm basically implementing what's up there. And then from here we get the next output and the final output here, and just following that, gives us the green, orange, yellow, and red. And this is an implementation of one-hot encoding. Later on we'll see the full encoding version of this and for Dflipflop, and see it with the Dflipflop and the JK flip-flop. But this is, as you can see, the outputs are simply coming out of the current state, and then we just and then we since the other thing that happens is, since we are only looking at the states where state variables are only one state variable is 1, then we can assume everything else is don't care. That allows us to get away with quite a simpler excitation input. As you will see later on, the complexity goes up. Okay, that brings us to the end of this particular presentation on one-hot encoding.